Hey kids, today we're talking more about gas laws and we're talking about some of the secondary gas laws, including Dalton's law of partial pressures. Okay, so these two laws were taught to you in honors, okay, and they can be written in two different ways. Okay, so first of all, if you have a gas mixture, okay, with different gases, the total pressure of the gases is equal to the sum of the partial pressures of each component. Okay, so P total is P1 plus P2 plus P3. That is your first equation. Okay, a second equation that is the same type of equation, just written in a different way. If you have a gas that's collected by water displacement, okay, the water vapor pressure must be taken into account to find the pressure of the dry gas. So you have a second equation called P total equals P dry plus P water. Okay, so for example, let me just take a minute to draw a little picture of that. Okay, if you have a beaker, or excuse me, a closed container, okay, and you are bubbling gas, dry gas through it. So let's say carbon dioxide. Okay, we'll draw the carbon dioxide in blue, red, and the water will be represented by blue. Okay. What happens is the carbon dioxide will bubble through, and then of course will be collected at the top. Okay. And then there will also, though, be at the top of the container water vapor too. Okay, so when you take the pressure, if you have a gauge on top, okay, that's going to be the total pressure. And that total pressure will equal that partial pressure of the water vapor plus the partial pressure of the dry gas. And in this case, of course, it's carbon dioxide. Okay, so that is our second equation. Now, in order to do this type of problem, you're going to need to print out your water vapor tables because at different temperatures, as you can see here, there are different water vapor pressures. So if you know the temperature, you can know the pressure. Okay, so you need to print out these water vapor tables, and I've given you a PDF of these. So if you want to pause the video now and print out this PDF of the water vapor, the water pressures, the vapor pressures of water, excuse me, at different temperatures, go ahead and do that now. And at any time when I'm doing the problems, if you want to stop the video and try it yourself and then watch the solution, I really highly suggest that. Okay, so we talked about total pressure equal to sum of the partial pressures, or the total pressure equaling the wet pressure plus the dry gas pressure. Now we have another formula called partial pressures with mole fractions. Okay, so sometimes you don't have enough information as you with using the first Dalton's law, and you need a second equation. Okay, so in this equation, you're going to be able to calculate the partial pressure of a gas when you're given the number of moles of each component. Okay, so the partial pressure of a gas, say gas 1, is going to equal to the mole fraction of gas 1 times the total pressure. Okay, now X is considered the mole fraction. That means the number of moles of gas 1 over the total moles is going to equal to the mole fraction of gas 1. Okay, and mole fraction, because moles cancel out, is a dimensionless number. Okay, so just to repeat, the partial pressure of a gas A is equal to the mole fraction of gas A times the total pressure, or in this case, 1. Okay, so what we're going to do now that we have 3 equations, we're going to look at different problems and do them together. Okay, and if you want to pause this video and do it yourself, or try it yourself, and then watch the solution, you can go ahead and do that now. Okay, in this problem, we have a 2-liter container of nitrogen gas at 750 millimeters of mercury, and it's connected to a 5-liter container of oxygen at 5 liters, or to a 5-liter container of oxygen at 325 millimeters of mercury. A valve between them is opened. What is the pressure of the system after the gas is diffused? Okay, so first, before we start, let's just draw a picture to make sure we understand what's going on. Okay, so we have a 2-liter container, and then we have a 5-liter container. And it's connected by a tube with a valve here. Okay, so we've got 2 liters and 5 liters. Now, once that valve is opened, okay, once that valve is opened, the gases diffuse together. Okay, and what we have to assume then is that now we have a total volume of 7 liters where the gases are going to expand. Okay, so the gases are both, if we have one of the gases being green, you know, the gases are in both containers. And one of the gases in red, gases are in both containers. So we have a total of 7 liters. Okay, so if we want the pressure of the whole system, the first thing we have to do is find the new partial pressure of nitrogen and the new partial pressure of oxygen at this new 5-liter volume. Okay, so the first thing we're going to do is use our fundamental gas laws in the last video. Okay, so we can assume a constant. So we have P1, V1 equals P2, V2. Okay, now let's look at nitrogen first. Okay, let's look at nitrogen first. Okay, and we want to know, okay, we have P1 over V1 divided by V2 equals P2. We want, remember, V1 is going to be 2 liters, and V2 is going to be 5 liters. And P1 is 750 milliliters. Okay, so we can plug in some numbers here, and we get 750 millimeters of mercury times V1, which is 2 liters, divided by our new volume of 7 liters. Okay, so actually I think I said P2 or V2 is 5 liters. It's actually the total, which is 7 liters. And you get a new partial pressure of 214 millimeters of mercury for N2. Okay, then let's say we'll take oxygen now and do the same thing. Okay, so we have P1, V1 over V2 equals P2. And for oxygen, it was 325 millimeters. Okay, V1 is 5 liters for the oxygen. Okay, and then once again, our total is going to be the same, which is 7 liters. And we get a partial pressure for the oxygen now of 232 millimeters. Okay, so now we have our correct partial pressures. And if we want the total pressure, we can use that first Dalton law, where P total is going to be P1 plus P2. In this case, it's going to be P of the nitrogen, okay, plus P of the oxygen. Okay, and that's going to be 214 millimeters plus 232 millimeters, okay, which gives you a total of 446 millimeters of mercury. Okay, so that's the pressure of the system after the gas is diffused. Okay, we needed the fundamental gas laws to start off to figure out the new partial pressures at the new volume. And then we needed Dalton's law of partial pressures to add them up to get the total pressure in the 7-liter volume. Okay, so let's look at this problem. We have a second Dalton's law problem. Okay, in this problem, we're going to determine the partial pressure of oxygen in a mixture of 37 grams of nitrogen and 80 grams of oxygen when the total pressure of the mixture is 900 millimeters. Okay, so we know the partial pressure, we know the total pressure, and we need the partial pressure. Okay, so we're going to probably need, since we can only kilogram, isn't it cool that we're going to use that equation of Dalton where we need total pressure, partial pressure of oxygen is going to equal the mole fraction of oxygen times the total pressure. Okay, and we have the total pressure that's given to us. So now we just need to look into getting the mole fraction of oxygen, which means we need moles. Remember, the mole fraction of oxygen is going to equal the moles of oxygen over the total moles. So we're starting out with 37 grams of nitrogen, and I'm going to set it up kind of like how I did with empirical formula, where I make columns. I've got 80 grams of oxygen. To get to moles, we want to have weight, so I'm going to divide by 28.02 grams per mole for nitrogen, and 16 grams per mole for 32, we've got 2 of them, 32 grams per mole for oxygen. Okay, when I divide this, moles of nitrogen, and I get 2.5 moles for oxygen. Now I'm going to solve for the mole fraction, okay, which is the formula right here. And I'm going to get the mole fraction of oxygen is going to equal 2.5 moles over the total, which is going to be 1.32 plus 2.5 moles. And moles cancels out, obviously. And our mole fraction comes out as 0.65. Okay. And now I'm going to plug it back in to my original equation. Okay. So my partial pressure of oxygen is going to equal my mole fraction, which is 0.65, times my P total, which is 900 millimeters of mercury. And when I multiply those two numbers, I get an answer 500 millimeters. So that's the partial pressure of oxygen. Okay, and at any time, if you want to stop this video and watch it again to make sure you understand it, you can go ahead and do that. Okay, next problem. Okay, determine the mole fraction of neon in a mixture that is at 1900 millimeters of mercury. Okay, the mixture also contains oxygen with a pressure of 560 and nitrogen with a pressure of 780. Okay, so this problem, I am given my total pressure. Okay, that's my P total. It says the mixture. Okay, so that's my P total. And I also have partial pressures of oxygen and nitrogen. Okay, so let's see, they want mole fraction, so let's take down the formula for mole with the one with mole fraction in it. So that means the partial pressure of neon is going to be the mole fraction of neon times the total pressure. Okay, well, let's see. we want a mole fraction. We have the total pressure, but now what we don't have is this partial pressure of neon. Okay, but we do have the partial pressure of the other. So we're going to need two equations here. We also have the other Dalton's law, which says Q total is going to be the sum of all the partial pressures. So that means partial pressure of neon, the mixture of three gases, partial pressure of oxygen, and the partial pressure of nitrogen. Okay, and we can solve for the partial pressure of neon. So we have the pressure total minus the partial pressure of the oxygen minus the partial pressure of nitrogen. It's going to equal the partial pressure of neon. Okay, now we can plug in. We've got 1,400 millimeters. Remember, that's the total that we got from the given. Okay, we got the pressure of the oxygen, which is 560 millimeters of mercury. And then we got the partial pressure of the nitrogen, which is 780. And that's going to equal our partial pressure, 560 millimeters of mercury. Okay? And so that's our partial pressure of neon. Now we've got our partial pressure of neon. We can now solve for our mole fraction. Okay, so we reconfigure this equation to solve for mole fraction. We've got the mole fraction in neon is going to equal the partial pressure of neon divided by the total pressure. We can plug in. The partial pressure of neon we've solved for is 560 millimeters of mercury. And the total pressure from the given is going to be 1,400 millimeters. And when we solve for that mole fraction, we get an answer of 0.29. And that is our mole fraction of neon. Okay, last problem. Okay, determine the water vapor pressure at 28 degrees. Okay, this right here. Oops. Okay. You are going to use your water vapor table, okay, that I showed you in the beginning to figure out that water vapor pressure at 28 degrees. Okay, and if you look it up, okay, the pressure of the water at 28 degrees in millimeters of mercury is 28.3 millimeters of mercury, and that's from the water vapor table, okay, that I've supplied you. That's the partial pressure of water. Okay. Now it tells you that carbon dioxide is collected over water at 28 degrees and at a pressure of 800 millimeters of mercury. Determine the mass of CO2 in the sample. The gas volume is 23.6 milliliters. Okay, so what does that mean? Okay, if I draw a picture, okay, like I did before, okay, you have your water, okay, and you're collecting gas over it. So you've got water vapor up top, we're going to use that as blue, and then we also have carbon dioxide. Now they tell us the pressure is 800 millimeters of mercury. That pressure is going to be the total pressure. Okay, so if you have a gauge here, it would be 800 millimeters of mercury. That's the total pressure. we want to know the mass of carbon dioxide. Okay, so we probably are going to use ideal gas law to get that mass, but the first thing we need is the partial pressure of the carbon dioxide. So let's take a look. Let's write that here. And we know this is a wet-dry problem. So our master equation is going to be total pressure is going to be the partial pressure of the water vapor plus the partial pressure of the dry gas, which is going to be, in this case, carbon dioxide. Now, we have the total pressure, okay, and we have the partial pressure of the water. We just looked that up in our water tables. So we can now solve for the partial pressure of the carbon dioxide. So if we rearrange this equation, we have the total pressure minus the partial pressure of water is going to equal partial pressure of carbon dioxide, which is what we want, because we want the mass of carbon dioxide. So we just want carbon dioxide. So that's going to equal 800 millimeters of mercury minus 28.3. Okay, and then we get our partial pressure of water equaling, partial pressure of carbon dioxide equaling 772 millimeters. Okay, so now we have the partial pressure of carbon dioxide. We have the volume, okay? We've got the temperature, and we want the mass. So we're going to use now the ideal gas law to get that. Okay? So I'm going to write down this number 772. That's our new carbon dioxide, and I'm going to erase everything else for now. Okay, so I know I have the partial pressure of carbon dioxide as 772 millimeters of mercury. I know my temperature, it's got to be in Kelvin. It's got to be 28 plus 273, which is going to be 301 Kelvin. I've got my volume. It's got to be in liters. So I'm going to make that 0.0236 liters. Okay, I'm going to use my R number as 62.4 because I need to match R to the pressure. And that's millimeters of mercury, liters over mole Kelvin. Okay, now I don't have number of moles, but I do know that number of moles is equal to the mass divided by the molecular weight. And I'm going to plug that into PV equals nRT. Okay, so PV equals nRT. PV equals mass over molecular weight times RT. Okay, and then I can rearrange this equation to give me, do it over here, mass equals PV times molecular weight over RT. And now I can plug everything in. And I'm going to plug in 772 millimeters times my volume, which is 0.0236 liters, times my molecular weight of carbon dioxide, which is 44.01 grams per mole, okay, divided by R, which is 62.4 liters times millimeters over mole Kelvin times 301 Kelvin. Okay, now let's watch the units cancel out. Okay, millimeters is going to cancel out with millimeters. Liters is going to cancel out with liters. Moles cancels out with moles. Kelvin cancels out with Kelvin. and we're left with grams. Okay, so when I multiply everything on top and divide everything on bottom, I end up with my answer being, I'm going to write it right at the top, 4.2 times 10 to the negative second grams of carbon dioxide. And that is the answer for this problem. Okay, so if you have any problems with that and need to watch it again, pause it, rewind, okay, and then you have a lot of practice problems that you can do to make sure you understand it. Thank you.